Very high speed reductions can be achieved by connecting several planetary drivers in series. However, the resulting system will require a relatively large number of gears and will relatively heavy. The harmonic driver is a simple solution for mechanical systems requiring a large speed reduction in a lightweight space. Speed reduction from 30 to 130 is possible in single stage. The function of harmonic driver is based on the principle of strain wave gearing, which require a flexible gear. The harmonic driver consists of three main components, as shown in this figure. Wave generator, flex spline, and the rigid circular spline. The wave generator is made up of the two separate parts, an elliptical disc called a wave generator plug and an outer ball bearing. The elliptical plug is inserted into the bearing, forcing the bearing to conform to the elliptical shape but still allowing rotation of the plug within the outer bearing. The flex spline is shaped like a hollow cup. The sides of the spline are very thin, but the bottom is relatively rigid. This results in significant flexibility of the walls at the open end due to the thin wall, and the closed side being quite rigid and able to be tightly secured to a sheet. For example, teeth are positioned radially around the outside of the flex spline. The flex spline fixed tightly over the wave generator, so that when the wave generator plug is rotated, the flex spline deforms to the shape of the rotating ellipse and does not slip over the outer elliptical ring of the ball bearing. The ball bearing lets the flex spline rotate independently to the wave generator's shaft. The circular spline is a rigid circular ring with teeth on the inside. The flex spline and the wave generator are placed inside the circular spline, meshing the teeth of the flex spline and the circular spline. Because the flex spline is deformed into an elliptical shape, its teeth only actually mesh with the teeth of the circular spline in two regions on opposite sides of the flex spline. They are located on the major axis of the ellipse. This video shows you how the harmonic driver works. The reduction ratio for a harmonic driver is given by these equations. where NF is the number of teeth on the flexible flex spline, and NC is the number of teeth on the rigid circular spline. Here, NC must be larger than NF. The input and output shaft rotate in opposite directions. For large reductions, we want the difference between NC and NF to be as small as possible. Also, we want the difference to be as small as possible to minimize the distortion and the stress in the flex spline. However, the difference needs to be large enough that two splines touch at only the ends of the major axis of the ellipse. Typically, the minimum difference is equal to 2. In addition to a very high speed reduction ratio in a single stage, harmonic drives have a number of other advantages over rigid gear drives. They have very low backlash and a very high position accuracy because they can achieve very high speed reduction ratio in a single stage. Harmonic drives are very small and lightweight compared to conventional gear reducers for given torque and power requirement. Because harmonic drives have concentric input and output shafts, they share the same center line. Harmonic drives also have very high torsion stiffness. The main disadvantage of harmonic drives is relatively high cost. Therefore, harmonic drives are used in high-performance applications. Typically, applications include speed reducer at robotic arm joints, solar array drives in space, satellite and space vehicles, aircraft position device, and machine tools. Until now, harmonic drives are a specialty item that is manufactured by a limited number of companies, mainly in Germany and Japan. Where we take about 8 weeks to talk about static dynamic force analysis for mechanisms. In this topic, we use 2 methods to analyze the force of the mechanism: free body diagram and the conservation of power. And then we talk about how to design the displacement program of the follower and determine the cam profile using the graphic method and the analytical method. Designed for spur gears to compute the dimensions to thickness of the spur gears and how to avoid interference and undercutting. Finally, we analyze the gear trend to figure out the gear ratio. I hope you can well know them by practice the problems of homework. The final exam will come in next week. All exam problems are chosen from homework problems. Of course, they will be with small changes. See you Wednesday. Bye-bye.